All right, people, we're back. We're talking about gravitational time dilation, all right? So I've drawn out two different roads here, all right? One road is going this way, and one road is going that way. Let's imagine that there's a car accident. Bam. This big giant metal thing represents a car accident. Now, cars going this way are just going to keep on going at the normal rate, right? Cars going this way are just going to keep on going down the highway. And let's say that we're actually standing right here, just watching, right? This is us. We're watching it all happen. Cars going this way are going to be fine. But the cars coming this way, as they get closer to the accident, they're slowing down, right? And then as they move away, finally they can speed up again. These cars are unaffected by the accident. This car, and really if we look at it this way, these cars slow down as they get closer. Let's look at it this way. Slow down as they get closer, and then they move away. All right? This is how we can think of gravitational time dilation, okay? As you get closer to an object with more gravity, the time that we perceive as this observer right here slows down, right? And now if you're in this car, okay? If you're in this car, everybody else is doing the same thing as you, so you don't really see that slowing down. Just imagine it like that, right? But as the observer, we can say, okay, we know this one's going slower than these. We can see the slowing of time. As you get closer to this car accident, as you get closer to the body of mass, your time will slow down due to gravitational time dilation. So let's look at that equation real quick. Okay, so here's the equation for gravitational time dilation. Now, I know it looks big and scary, but it's okay. We'll go over every single part of this, and you'll understand it, and you'll know it, and you'll practice it, and you'll be great at it. Now, the important thing to remember about time dilation and understanding changes of time due to different variables is that you need to compare it to something. Time dilation means nothing if it's the only clock, right? If we go up into outer space and we get affected by gravity somewhere, our clock is still going to run at the same time. Like, we're not going to see ourselves in slow motion doing all this. No, we're going to experience it as we normally should. But to somebody else outside of the influence of the gravity, they're going to see us, affected differently. So that's what we have to do. That's why there's two T's right here. There's T prime, and then there's regular T. And T prime is the time within the gravity. So here's what I'm going to do. I'm going to actually change this. And really, let's even forget about this delta right here. Delta just means change, right? But we'll just forget about that. And we'll just make it even easier. We'll say time in the gravity is equal to time regularly, right? Time that's uninfluenced by gravity, multiplied by the square root of 1 minus 2 times the universal gravitational constant, the mass of whatever object we're on, how far away we are from that center of gravity, and the speed of light squared. Okay, so again, the time that's being affected by gravity is equal to regular time multiplied by 1 minus 2. G, we know, is equal to, oh, you guys can't see that. Let me zoom out a little bit. G, we know, is equal to 6.67 times 10 to the negative 11. M is just the mass of the object, okay? R is how far away it is, so just mass of object. This R is how far away from center of gravity, okay? And this c squared is the speed of light squared. We haven't talked about this yet, but it's the speed of light. C always represents the speed of light. So c squared is equal to, well, c is equal to 3 times 10 to the 8th meters per second. Okay, so if it's c squared, it's just this value squared. So c squared is equal to 3 times 10 to the 8th squared. So that's how you look at this equation, okay? So we're going to give you a couple of practice questions, and you'll practice it in the Ed puzzle.